Hi, everyone. Welcome to the February Interdisciplinary Instrumentation Colloquium. Before we get to the main event, I just wanted to take the opportunity to thank our outgoing speakers committee for 2025-2026. We had Richie and Peter from the physics division and Jan and Jinsei from MBIB. And I think you'll all agree with me that it was a really interesting range of diverse talks last year. We had a bunch of different things, including quantum sensing, molecular biostructures. We had lots of microscopy and imaging stuff. And then the last couple of talks, we've been hearing about light sources. So if you could just all join me in a round of applause for our outgoing committee. Thank you very much. All right, and with that, I'm going to pass it on to Jan to introduce our speaker. Thank you.
Yeah, welcome everyone in the room and online. And yeah, today I have the pleasure to have Georgi Dakovski here from LCLS over on the other side of the bay at SLAC. And it's really my pleasure to introduce him because I've been working with him for many years, maybe 12, 14 years ago. We started working on a lot of experiments at the soft X-ray instrument at that time at LCLS. And Georgi was really instrumental pushing the experiments at that beamline at that time. And then over the last more than 10 years now, developing the new instruments that are focused on soft X-ray spectroscopy at LCLS-II. And they came online recently over the last 1.5 years. And it's really great to have him here today to tell us about the development there, the capabilities and the experiences of the first experiments there. And I want to mention Georgi has been not only at LCLS, but he initially did his PhD in Case Western and then a postdoc in Los Alamos, already working at photoemission spectroscopy, and was really pushing spectroscopic methods to study exciting phenomena in material science and chemistry for a long time. And so it's my pleasure to have him here today and tell us about the exciting new things that can be done at LCLS now in the soft X-ray regime and maybe future perspectives as well. So thanks a lot, Georgi, and looking forward to your talk.
Thank you, Jan. It's a pleasure to come to Berkeley Lab. I haven't been here in quite a few years, but it's always wonderful to come and share a few of my thoughts about where the soft X-ray program has been going for the past almost 15 years, I would say. As Jan said, I've been with LCLS since 2011, so coming up on 15 years. For the first 5 years or so, I was mostly a beamline scientist and supporting user instrumentation at the soft X-ray SXR beamline. And then about 10 or so years ago, when we started planning more and more about LCLS-II, the new superconducting machine and the new instruments that we'll build, I jumped on that train and I've been there ever since. So my talk is not too scientific. It actually barely is at all. I just want to kind of tell you a story with a lot of pictures. There are some instrumentation and engineering curiosities that I hope might be interesting to some of you. Probably most of all, I would be happy to just get questions and answer your questions and maybe come back here for another talk sometime in the future. So anyway, first I'll just start with some brief motivation, then some of the requirements that we set forth at the very beginning, followed by some explanation about the beamline and the two instruments that are currently stationed there, chemRIXS and qRIXS. Some first results from the last year or two, as Jan mentioned, and then maybe a bit of a look into the future. So as I said, I come in from the soft X-ray beamline at what used to be at LCLS. And for those of you who have maybe no idea what that was the monochromatic soft X-ray beamline that didn't really have any permanent end station there. So we would bring in equipment from really all over the world, including the RSXS chamber that used to be built here by Ide Chuang and Zahid Hussein many years ago. We would bring in the liquid jet end station from Berlin. So we would do all sorts of experiments. Probably the first example is from a surface science experiment where we would look at the X-ray absorption and emission of carbon dioxide depositing on a clean ruthenium surface. Then there is another example where we are, for example, tracking the magnetic peak of terbium manganite. And you can see how the peak really follows closely the oscillations of a strongly applied terahertz electric field, and the oscillations goes away above 30 Kelvin, which corresponds to some transition temperature. Another example would be looking at the magnetization dynamics. In this case, it's a gadolinium ion cobalt film, which is known that it switches polarization upon optical excitation. So we can track the dynamics of the magnetization both at the iron and the gadolinium edges, and you can see how fast they switch and how long the whole process takes. And finally, some of our better known example is for studying iron pentacarbonyl, where we can actually track the excited state dynamics in the system by collecting a full 2D RIXS maps. And these are, of course, wonderful experiments, but the common thread behind all of them is that they were heroic, extremely heroic, because for anybody who has done soft X-ray experiments, especially at an FEL, those experiments are challenging. The photon yield is very low. You need to collect a lot of statistics, and FELs are not really known well for instruments that are stable and you can collect a lot of statistics very easily. So, but really it was this kind of pioneer experiments that ultimately led LCLS to push for a high repetition rate machine. And that's why LCLS-II and nowadays LCLS-II HE are being built. So you may have seen these plots elsewhere, but on the left-hand side, you see basically the justification behind LCLS-I, if you will, which was our old copper LINAC source, where you really get a tremendous boost in terms of peak power because we get these strong millijoule level pulses. But then we really wanted to move into the high average brightness, which can only be achieved by getting the high rep rate beam. And this was the motivation for the superconducting development. And up to 10,000, well, the rationale there is that we still work most of the time at 120 hertz, the copper machine, but the new superconducting machine has been designed to reach up to a megahertz. So a few pretty pictures from the decade-long project that LCLS-II was. Finally it's over. But yeah, you can see on the left-hand side the accelerator, which was a big part of it got ripped apart so that there'll be a new cryo modules installed there. There's actually a whole new cryo plant built that can circulate the liquid helium needed to cool down the niobium cavities. And we, of course, got tremendous support from many other laboratories, Berkeley, one among them, especially when it came down to building the soft X-ray undulators that you can see on the left-hand side here. And all told, sometime in the last year or two, we actually completed the whole upgrade, and we were basically running both a superconducting LINAC at around 4 GeV, in reality maybe about 3.75, that was feeding all the soft X-ray instruments through the soft X-ray undulators. And then we also kept, of course, running the copper LINAC, which would feed our hot X-ray suite of instrumentation, which is, of course, awaiting their upgrade from HE. So HE stands for high energy. That's an upgrade that's going on at the moment. And what it really amounts to is basically adding more cryo modules so that the electron beam energy can be upgraded from 4 to around 8 GeV. And then there are fast kickers that can spread the beam, basically at any arbitrary rate to any of the undulators, soft, hard, and that's how we plan to do experiments. So as I said, currently we're in this process right now of upgrading the machine to the AGV, HE parameters, and we hope to get there by October of next year. But we're currently not close. Again, the copper LINAC is still working and all the instruments are open for business. As a matter of fact, if you hurry up in about 28 hours, our submission deadline for the next run will expire. So if you want to submit a proposal for what is going to be run 27, there's still a little bit of time. Okay, and then this is an overview of kind of the suite of hutches that we are housing. For those of you who haven't been there, you can see the 2-mile-long LINAC. After that, the beam goes underground once again and into the undulator hole. And finally, there are 2 experimental holes, the near and the far hole, that house overall on the order of 10 experimental areas. Historically, the near hole has been dominated by soft X-ray instrumentation, apart from XPP, which has been our hard X-ray pump probe suite. And what's new for the past 5 years is, of course, we have now emerged on the second floor. And by we, I mean the qRIXS beamline that I was in charge of. After taking a long, hard look, it turned out that there is not enough space on this ground floor, or basement floor rather, to put all the new instrumentation that we had intended to build. So we decided to look into sending the beam on the second floor, and that's where we are at the moment. Excuse me. Okay, so just a couple of slides about what is the scientific motivation behind the new beamline, but also the instruments that we were building there. So there are 2 instruments. One of them is qRIXS, and that's an instrument that's really, as the name suggests, designed towards employing high-resolution resonant inelastic scattering to study correlated materials. So correlated materials is really a broad term to describe materials where strong electron phonon, electromagnetic interactions are dominant. And what they're really very useful and interesting about is that you can actually engineer many properties on demand. Those materials tend to respond very strongly to external perturbations, and at LCLS, that's our bread and butter, right? We photoexcite samples, wide variety of wavelengths or magnets, and then we study how the system evolves in time. All this can let us, of course, try to understand long-standing puzzles in some of these materials, be it high-temperature superconductors or colossal magnetoresistance or phase transitions in various systems. But sometimes it's to actually engineer new functionalities through light-matter interactions. On the chemistry side, the chemRIXS instrument, again, resonant inelastic X-ray scattering, but in that case, the samples of interest are condensed phase chemistry systems that are usually delivered in the form of liquids. Really, the interesting questions there are more in the realm of maybe photocatalysis, where photoexciting the sample may actually drive the system across some otherwise high energy barrier and into a desired product that you wouldn't otherwise get in nature. But you want to be able to be chemically and atomic specificity so that we can, actually probe which atoms are participating in all these reactions. So there are, of course, a myriad of questions that might come to mind why it's important to study those materials. I'm not going to list all of them and go through them necessarily, but what I would focus for the moment is the fact that all these questions can really be addressed only if you have high energy, momentum, and time resolution spectroscopic techniques at your disposal. You need a really high coherent flux. For the time being, we measure that, let's say, in terms of photons per second per milli-electron volt. Especially in the realm of quantum materials, polarization control is quite important. This allows you to kind of play with the scattering cross sections or to study magnetism. And I have a few more examples further down in the presentation. And again, tailored, especially optical excitations, are crucial both for the chemistry and for the material science communities. Chemistry case, you might want to mimic nature, so you might need to generate green light, so you need a visible OPA. For the material science community, those people tend to be more interested in mid-infrared or terahertz excitations, where you can directly deposit energy in the lattice rather than the electronic system and so forth. Okay, so a few words. I've kind of drummed the beat qRIXS a few times, but in case you don't necessarily know all the details, it's essentially Raman scattering with X-rays that is particularly well suited for studying low energy excitations in wide variety of materials. It's one technique that gives you a tremendous amount of information on resonance. You can kind of going clockwise from here, you can see this zoo of excitations that you might be able to see in your sample in terms of kind of increasing energy scale. And a lot of those have already been observed in the past 10 or 15 years. The resolution in quite a few facilities has reached on the order of 20, 30, 40 MeV, which is kind of on par with the elementary excitations in a lot of these systems. So you can see phonons, you can see charge density waves, you can see plasmons, you can see dispersing excitations at higher binding energy, which in this case are orbitons. And this, of course, beautiful kind of excitations here are magnons that you can map out all the way to the edge of the Brillouin zone. So extremely powerful technique, very well suited for FEL. It's a photon in, photon out technique. So highly useful for us. Okay, so a few words about the beamline that we built. So kind of at a very high level, we wanted a soft X-ray beamline that will go from just below the carbon edge to about 1.5 keV, with the rationale to cover, of course, the carbon, nitrogen, and oxygen edges for our chemistry community largely, but of course, cover also the 3D transition metals and the M edges, M4, 5 edges of the rare earths. But there's a lot of course, transition metal oxide, magnetism, and all that. We wanted to have two kind of at a high level, two sets of modes that we can set up our monochromator. We can either get to a really high resolving power that's needed for qRIXS, or in the future for electron spectroscopy. But we also need to have the option to kind of go to a really low, relatively low resolving power of 2000, which is kind of on the order of half an EV and below, which really suffices for a lot of the chemistry experiments. But in that case, you get a lot less pulse stretching, so you can actually maintain a very high temporal resolution with a decent energy resolution. We needed to have a very variable kind of spot size. That's important because we really have one branch to the beamline. So as you see later, the two instruments are one after the other. So you need to be able to focus the beam selectively either in one location or the other. Also, you sometimes have to mitigate sample damage by elongating your beam along one way or the other. So we use the bendable KBs, which are working quite well. And of course, half of the experiment is really kind of setting up for the optical laser to the correct wavelength, to the correct post-duration polarization, and so forth. So as I mentioned before, for the correlated materials community, the wavelengths of interest tend to be between the visible and the terahertz, while for the chemistry community, it's usually UV to vis. Okay, this is kind of a cartoon, the picture of how the beamline works. So I'm not going to go necessarily through all the components, but the first three optics basically comprise our monochromator. They are all pointing upwards. Eventually, the beam gets deflected by something of the order of 7 degrees. And after it propagates to about 20 meters, it gets vertically focused to the exit slit location here, which happens to be on the roof of the hutch that's actually underneath us. So really inconvenient place. But after that, the beam emerges, and through three optics, two of them being the KBs, the beam kind of gets back again parallel to the floor. And I'll show you some images from how the hutch layout happens to work. Yeah, this is more of a kind of a CAD view drawing of what I just described. As you can see, we actually have 3 pipes here. We decided that there is some potential in the future to upgrade to more than just having 1 branch, but to have actually full 3 branches. We're, of course, far away from actually making that a reality, but given that we had to drill through a 1 meter thin concrete over, you know, a 7-degree angle, we decided that that's a very invasive procedure that we had to do early on while the construction was going on. So we had those holes drilled and pipes installed, and right now they're just blanked off, but maybe sometime in the future we'll be able to expand our hutch and house more instrumentation. This is a slide from Daniele Coco, who was the optical designer of the beamline and especially the monochromator. This is a lie. Everything you need to know to operate the mono, that's not true. There's a lot more that you need to operate the mono, but that's what Daniele thought that would be useful to me. Anyway, the monochromator is a very kind of I would say unique design because there are a lot of flexibility built into it, which is to our advantage, but it also makes it somewhat challenging to set up right away. We first start with this elliptically curved optic, which actually has in-vacuum benders, which actually work phenomenally well. So we can actually control where the beam is focused without changing the angle of the mirror and without changing kind of the way the monochromator is actually tuned up. And then we have a flat pre-mirror, which rotates around some virtual axis here, and you can basically change the incident angle on the grating, and the grating is typical VLS grating that, yeah, we have 4 of them that, you know, one of them allows us to get to this low energy resolving power of around 2000 for the chemistry community, and there are 3 higher resolution gratings, densities from 300 to 700 lines per millimeter, and those are for the condensed matter community. And that's an image of how 3 of those gratings look like. The beam kind of comes somewhere from the bottom, and the pre-mirror is currently hidden here, but you can see the gratings on a cradle that yeah, you can imagine how the beam kind of reflects and going through here and down to its path on the beamline. Okay, we spent quite some time thinking about diagnostics on the beamline that can help us understand if the beam and ultimately if the you know, not just the position but the energy of the beam is drifting, especially given the fact that it was a new LINAC, first of all, so we cannot really tell how well and how stable the beam is. So that's problem number 1. Then we have 3 optics all pointing upwards, so each one of them might contribute some drift of the pointing of the beam. Then one part of the beamline is sitting in the basement, another part, the exit slit, is sitting on the roof of another concrete slab in the building. So there was the potential of a lot of moving parts that can actually disturb the performance of the beam. So we decided to kind of have some diagnostic beam that we can send towards a photoelectron analyzer that can slowly accumulate data and either look at you know, a core level peak or maybe at the Fermi edge if we have enough counts, and basically to track the absolute energy of the beam that passes through the exit slit, so that for us to have a diagnostic to maintain kind of the same performance of the beamline. So the way that we get that diagnostic beam is actually through our exit slit, which is not exactly 2 metallic blades that you might imagine, but it's actually 2 polished crystals that have a very sharp edge that works like a exit slit, but they also have a, you know, a surface that's kind of polished to a almost mirror shine, and its projected area, it's basically on the order of the width of the exit slit that we normally use, which is kind of on the order of 10 to 20 microns. And once you close that slit, and you know, we have independent ways to kind of control the pitch of these blades, you can generate two X-ray reflections, which propagate at a very small angle, but once they emerge upstairs, they are separated by a few centimeters. So you can have your directly kind of transmitted beam here go to the experiment and have two reflected beams that you can use to diagnose. And we tried that system. It actually works quite well, but we tried it with our low repetition rate beam. So it wasn't necessarily useful because for photo emission experiments, we have to attenuate the beam a lot so you don't get space charge. And we really hope to put that in more use with the superconducting beam. Okay, so here is how the beamline looks once it emerges on the ground floor, which is where the hutch is. We have actually a very spacious hutch, which is wonderful. Yeah, the beam comes from left to right. The first end station is the qRIXS end station. We can see this on the order of a 6 meter long spectrometer arm that can rotate on top of this granite shelf here. About 6 meters downstream of qRIXS is where the chemRIXS end station is. This is actually technically the first end station that we brought online because it was somewhat easier to put together. And then maybe another 6 or 7 meters downstream, we actually have an empty port where users can bring their own end station. And we're currently in communication with 2 different groups to see if they can actually bring their, more dedicated and specialized instrumentation on the floor. Everything that's kind of below the beamline here, we have a raised floor, and underneath the raised floor, there are transport pipes where the laser is piped in from our neighborhood lab. And these all are laser tables here. Each one of them is dedicated to its own instrument. So again, qRIXS, for example, cares more about long wavelengths. So they have a mid-infrared OPA and a terahertz setup. chemRIXS cares more about the UV visible, so they have a visible OPA to tune the wavelength. Currently, the third end station laser table is empty, but we hope to change that soon. Okay, and this is actually a photograph of the beamline on the other side. Why do we have a cowhide here? I don't exactly know, but one engineer came and left it, and it's been there ever since. All right, so a few words about the design of the end stations. So chemRIXS was the one that came online first, so I'm going to say a few words about that. Again, deceptively simple in terms of concept. It's a chamber for basically injecting liquids in a high vacuum. So we would focus the X-rays onto a sheet jet, and I'm going to tell you a few more words about the sheet jets a little bit later. Part of the beam will go through, and we can measure basically X-ray absorption directly in transmission mode. Whatever fraction of the beam gets absorbed, you can then measure the fluorescence either in a total yield, or you can measure the inelastically scattered X-rays from that sample. And the chamber is really built around the idea to make all these measurements happen at the same time, so that you can optimize really as much information as you can in one measurement. This is how, again, the chamber looks from kind of a CAD perspective. The beam comes from the left-hand side. There is a whole granite section in front of it that basically it's a big stand that houses a few kind of critical components that are needed to make that end station work. We have an arrival time monitor, which is basically our instrument that tells us the exact kind of arrival time between the lasers and the X-rays. Unfortunately, that's not rock solid. That has a small jitter on the order of 100 or 200 femtosecond. For some experiments, that's okay, but for others, it's not. So we need to be able to correct that. Then the chemRIXS end station is this big vessel here, which is kind of on the order of a cubic meter, surrounded by all sorts of pumping capabilities. We had about 2,500 liters per second pumping capability coming from turbos, and we have 2 cryopumps on top of the chamber. So those are liquid nitrogen kind of cylinders that we can insert. Once they collect all the ice and all that, they can be retracted and then can be regenerated by just pumping on them, and we can insert them one at a time. And then what's really cool is we have actually a load lock chamber that's this vessel hanging behind them, and I'm going to have a few more pictures with that later. But that allows to really swap samples, and especially the microfluidic chips that we use to basically spray the samples into our vacuum, which tend to clog and break every now and then. And so that we would avoid venting the entire chamber, we built this load lock system. This is a really busy photograph of the chamber inside, but what I'll tell you, and you have to trust me on this, is that the optical and the X-ray pulses come from the left-hand side. They pass through a tiny mirror here, and the interaction point is somewhere here. This vertical structure here is the nozzle. You can see the tubes that carry the fluids that eventually get to this glass nozzle at the bottom. What's coming from the bottom part here, this cone structure, is a catcher and a recirculating system, which comes in very handy because then we can actually bring the sample back up and recirculate it. You can see some suite of avalanche photodiodes in the background. You see several YAGs here that are typical ways for overlapping X-ray and sample and laser beams. Yeah, and this is a kind of a nice photograph of our microfluidic chips that you can see on the left-hand side, and thin sheet jets that emerge from there. So that's something that SLAC and LCLS has been kind of investing for quite some time, because it's a extremely powerful and useful development that helps both our hard X-ray but now soft X-ray communities. Actually, Jake here in the audience is someone who spent quite some time developing this capability. And you can see the very thin kind of laser machined, I think, channels cut into this microfluidic chip. That's where you have high pressured fluid come together and then form this beautiful diamond looking sheet that most of the fluid goes around the corner, but the sample that you really care about is in the middle, and it's extremely uniform and can be down to hundreds of nanometers thick, so actually useful for soft X-ray experiments. And someone made this kind of a beautiful demonstration of how we circulate the sample, but yeah, we have this convoluted system of pumps and valves and vessels, but they all have to be operated kind of in a very precise sequence. But ultimately, what it all tells you is that if your sample can be recirculated, that means it's not really destroyed by the exposure to the laser beam or to the X-rays. Then you can really use kind of only tens of milliliters and recirculate them back and really keep running the experiment as long as you want. Okay, and then here are some of the pictures of this jet and how it actually looks inside the chamber. Again, you can see the microfluidic chips. You can see this beautiful thin leaf, and all going inside a catcher. Kind of to give you a scale, probably the distance between the nozzle and the tip of the catcher is on the order of 2 millimeters. The opening of the catcher is maybe 0.5 millimeter or so. And all of this runs into vacuum. There are no windows to separate us from the rest of the beamline, so we actually have to pay a lot of attention, making sure that the pressure both before and after chemRIXS stays really good. Okay, and yes, I mentioned a little bit earlier about the load lock mechanism. So when we were building the chamber, and we had eventually there is going to be quite a big vessel, as you can see. It's again on the order of a cubic meter. We didn't want to have to vent the chamber every time that something goes wrong, and something goes wrong pretty frequently with these microfluidic chips. They can get clogged, they can get broken, you have to replace them. So when I presented this problem to our engineering team, they came up with a solution called the Geneva mechanism, which I guess comes from the fact that this is what mechanical watches use. But it's really this rotating wheel here that a notch goes into this rail system, and then the whole wheel slides over and moves around. And what that gives you the advantage is that you can actually have two of these rail systems, and if you match their distance and their separation really fine, you can have a gate valve that can close in the middle. And that can, of course, allow you then to retract your sample, close the gate valve, vent the load lock system, but keep the main chamber under vacuum, do repairs, pump, and bring the sample back in. So it's relatively complicated, but after we aligned it quite a few years back, we haven't really had any trouble. And again, it allows you to replace samples in well under an hour, which is something that we couldn't really say back in the day in SXR, where every time the system clogs up, literally 10 people have to go inside the hutch, vent everything, open up flanges, and do repairs and all that. Right now, one or two kind of highly skilled people can do that in quite a short amount of time. Okay, and then a few of the early results from chemRIXS. So chemRIXS went through kind of this progression of commissioning, followed by what we call the validation experiment, which is an experiment that tends to be that we have a high confidence that it will succeed, and then we go to an early science experiment, which is an experiment that we have kind of invited the community to participate if they wish to do so. So the validation experiments that we did in chemRIXS involved really a strong field ionization of water. This was what you see on the left-hand side are actually data from an experiment that we did in SXR. Again, strong field ionization in water that Linda Young did quite a few years back. And what I'm showing you on the right are really, the same RIXS maps, but this time collected to the same signal-to-noise ratio in about 10 times less time necessary to do that. And that was, of course, in the very early days of chemRIXS and the machine. So since then, we have actually improved the performance even more. What you can see on the bottom right panel is, of course, the dynamics that we can measure in the first several picoseconds after we photoexcite the sample, and we stay at this resonance here. So yeah, what's I didn't mention that what's circled here is basically the new absorption peak that you basically create in water when you do multiphoton ionization. So that creates an absorption channel nominally that you don't see because it's below the edge. And in this case, we can actually do RIXS while we park the photon energy there. Then the early science experiment was actually, conceptually a similar idea, but in this case in fairly concentrated pyrazine. And in that case, we saw this is actually a RIXS difference map. So difference is what we actually measure in pretty much all the experiments with and without the laser. So you can see this extremely strong anti-Stokes component that we can see. For those of you who may have done RIXS, usually takes, let's say, 10, 15, 20 minutes to collect a quality spectrum. We can see this anti-Stokes feature in real time, basically in our live kind of data integration system by just looking at the camera that integrates for a second or two. We can see this peak. We can actually find our time zero by changing the delay and seeing when the peak would disappear, or I think we even optimize the spatial overlap, again, looking in real time. So that's truly something that we could not have done anywhere even close in the past. And right now, we can collect this data really in a matter of several minutes. So it has worked really fantastic. And yeah, finally, a shout out to the major instrumentation that we used in chemRIXS, especially in the early going. It's a portable VOS spectrometer that was actually designed here from Idi and Zahid Hussein again many years back. It's been our workhorse for quite some time, and we just very recently replaced it with another VOS spectrometer that just better optimized for chemRIXS because it has a bigger grating and a much larger camera, so the throughput is better. But yeah, this spectrometer has been a workhorse for us for quite a few years. Okay, so where is chemRIXS going in the near future? So again, there are plenty of scientific opportunities that we would like to exploit. Of course, we to make the best use of our machine, we really need to kind of develop this beamline into really the brightest soft X-ray beamline in the world. And there are quite a few possibilities there. We can go to higher rep rate. We can develop a self-seeding that can kind of shrink the bandwidth and give us more energy, more monochromatic photons. Excuse me. We're still quite a ways away from kind of being into the time resolution limits that we really want to be. So we would like to be in the tens of femtosecond range, and right now we're maybe close to 100. So there's a lot of investment that we need to make into kind of stabilizing our timing performance. Of course, so far, the experiments that have been successful in chemRIXS have used somewhat more concentrated samples, let's say 50, 100 millimolars. And of course, that community would like to go into a more dilute regime. So we need to have higher sensitivity. We also saw quite a bit of interest into novel nonlinear approaches to do science, especially with attosecond pulses. There was a strong collaboration with, again, Jake and other scientists here from LBNL into developing second harmonic generation to study liquid interfaces. There's another experiment that employed the coherent bandwidth of an attosecond pulse to study impulsive stimulated Raman scattering. And yeah, over the years, we are always kind of getting interest from people who want to study nanoparticles or thin solid films and all that. So if there are ideas, please reach to either me or Christian Kunus, who is the instrument lead for this instrument. Okay, and then a few words about qRIXS, which is the material science high resolution spectroscopy instrument. Again, conceptually, it's not that complicated. The beam comes in from the right side. The sample is inside this, again, relatively big chamber. But of course, in order to reach the resolution that this community cares about, which is, again, on the order of tens of milli-electron volt, we needed to have a large case spectrometer. And in that case, we have about 6 meter long arm that can rotate over more than 100 degrees in the scattering plane here. So a few details. Inside the sample chamber, we have an in-vacuum diffractometer. That's actually a commercially available system from Huber that works extremely well. We have 6 degrees of motion and really kind of precise positioning of the sample. The sample is, of course, connected to a cryostat. Most of the experiments are done at very low temperatures. We have a load lock to, of course, bring samples in from the outside. And really what kind of separates conceptually this system from chemRIXS and some of the other systems that we have here is that the long wavelength radiation that this community cares about, they really need large optics close to the sample so that they can get focused well. So we actually reserved pretty much a quarter of the chamber for the laser kind of laser paths that all need to converge onto the sample. And that's what really makes the system kind of very unique and quite complicated to operate. As you can imagine, there are multiple opportunities for collisions and all that, but ultimately we we actually have used pretty much all the infrastructure inside for experiments, and it works well. Just a few words about the spectrometer arm. We have an optics tank that we have one horizontally collimating parabolic mirror that allows us to kind of capture as much beam in the horizontal direction as we can. And then the gratings are pointing downwards. Currently, we only have one grating, but we're excuse me, hoping to get a higher resolution grating in the next 6 months or so. The design is again something that Daniele started quite a few years back, but got finished by Joe Dvorak, who is an optical engineer at LCLS II, and it really relies on the fact that we need to use a single spherical blaze grating, and we can actually cover a fairly short travel range, but go to different diffraction orders. And this way we can get to better and better resolution without necessarily kind of traveling over a long arc. I'm not going to bother you with all the details, but this is how the optics tank looks like. What you see, the gold here is the parabolic mirror, and the grating is pointing downwards. Why do we decide to point downwards? Is we were kind of initially very much aware of the fact that not being on the ground floor makes us somewhat susceptible to vibrations. And we really didn't want to put the detector 3 or 4 meters up in the air. And we actually decided to invert this and point it down so everything is close to the ground. So similarly to chemRIXS, here are some of the very early results that we got in qRIXS literally in the last 12 months. This is with the machine operating at 33 kilohertz, so some 300, a factor of 300 or so improvement based on what we used to do it back in the day in SXR with the copper beam. So what you can see on the left-hand side is what, tried to demonstrate as early as possible is what is the ultimate resolution. So we are very happy that for the current grading that we have in our spectrometer, we can achieve better than 10,000 resolving power. So on the order of, let's say, 50-ish MeV at the oxygen edge. And this is really kind of close to our design specifications, and what really opens up this instrument to the wider community, because that's the scientific kind of performance that they were expecting from us. The plots kind of in the upper right corner this is really our first time resolved data that we measured. What we're looking here is basically this is the elastic line of a signal coming from LBCO superconductor, and at about 1.7 EV loss, those are the DD excitations. Excuse me. And you can see that upon the arrival of a laser pulse, there is a prompt decrease of the intensity of the elastic line, which recovers on the order of a few minutes, a few picoseconds. So again, this is a time resolved spectrum that we can accumulate on the order of just a few minutes, which was truly unheard of before. We welcome users in runs 24 and 25, and all of them came home with some results which made us very happy. As a matter of fact, these are the first happy users. You can see Thorsten Schmidt in the center. Yeah, this is a table here that shows you the resolution that we got across the energy range. And one of my favorite spectrum here is the kind of vibronic progression in hexagonal boron nitride. That's one of the experiments that we did. And, of course, this progression can tell you quite a lot about the electron-photon coupling in this material. Okay, so coming close to the end, where are we going from here? Well, with qRIXS, again, our motivation is, of course, to develop qRIXS into the brightest beamline in the world. And we really want to improve our energy resolution. We have as I mentioned, new grating that we hope to give us maybe about 30,000 resolving power. So even better than what we can do today. Another priority for us is to kind of collaborate with our accelerator division to deliver variable polarization pulses. I know that's something standard at synchrotrons, but not so much at FELs, at least not at ours. We hope we can give that to users in about a year or so. We have to continuously, of course, improve our photo excitation methods and methodologies to kind of meet the demands of our users community. I didn't say much about this, but we have kind of a strong interest in developing X-ray photon correlation spectroscopy, which is a very, very photon-hungry technique that can truly benefit from the high rep rate. We are relatively kind of well on our way to make that kind of a viable approach in the hot X-ray regime, because of course with crystal optics you can play with a lot of kind of different delays that you can access very easily there, but in the soft X-ray domain it's somewhat more challenging. But Joshua Turner, who's been involved in a lot of experiments here at Berkeley, but also for the past 15 years at LCLS. He's driving the development of the soft X-ray capabilities, and we're really eager to kind of get a new beam and really demonstrate what we can do there. And of course, users always ask us for more innovative sample environments. Can we bring a magnet? Can we bring a strain cell and all that? So we're always looking to diversify there. Just a few slides about the different possibilities that we can use polarization control. We can study chirality, which recently has been a kind of a topic exploding in the RIXS community. People have seen chiral phonons in variety of systems. So now there is all sorts of ideas how you can potentially control and learn something new about those systems. Of course, with polarization control, we can study magnetic structures. In this case, you can see this beautiful skyrmion lattice that forms in a particular point in phase space. You can also study new forms of magnetism, like outer magnons in magnesium tellurite, or you can try to investigate the kind of band topology, if you will. So yeah, this is probably one of my last slides here, again, telling you about kind of what kind of information we can get with X-ray photon correlation spectroscopy. As a matter of fact, this is not a cartoon anymore. We have currently this little end station built specifically to allow us to park it on the qRIXS spectrometer arm, so that if we want to study some dynamics, let's say of magnetic peak close to a phase transition, we can actually disconnect our inelastic scattering spectrometer, move it a little bit to the side, not completely out of the picture the way it's shown here, but then put a detector far away, and we can measure the correlated kind of speckle pattern and really study the dynamics of heterogeneities. And sometime probably when the new superconducting beam arrives, as I mentioned earlier, we want to bring in a user-supplied end station. This one is particularly exciting for us because it can kind of give you information both about valence, but also core level excitations. We can, of course, utilize the uniqueness of our soft X-ray source, the fact that we can go on resonance, we can study complex oxides, buried interfaces, and maybe if we have even higher photon energy, we can do X-ray photoelectron diffraction, which can tell us something about the local structure in kind of variety of systems. So it actually provides a complementary tool to resonant inelastic X-ray scattering, and we really hope that in time we can kind of develop both the end station but the community as well, so that maybe they can do experiments half of the time on qRIXS, and then go to this experiment and to this end station and really look at how the electronic structure evolves in time as well. And then, yeah, as I mentioned before, right now we find ourselves at the beginning of this long downtime, which is going to last until October or November next year. And hopefully by the start of 2028, we are back in full force with high repetition rate beam. In that case, of course, it will also extend to about 8 kV. So our colleagues in the hard X-ray community will be rejoicing. But that brings me to the last slide where, yeah, I want to say that, first of all, I need to thank, I mean, there are on the order of 20 people here, but there are more like maybe 200 people that have contributed to this large effort. And yeah, chemRIXS and qRIXS are normally open for users. So if you have any questions, I'll be happy to answer. My last slide is just a picture of an excited instrument scientist and controls and laser scientists, and yeah, everybody that's very closely associated with this beamline. Thank you for your attention.
Yeah, thank you very much, Georgi. And we have time for a few questions.
Yes, right behind it.
So, yeah.
Thanks for the talk. A couple of questions around slide 42. First, you mentioned a flux of 10 to the 12 per ME. Yeah.
Yeah.
Where is that flux at?
That's at the sample.
At the sample. And what's the typical efficient kind of collection efficiency you have in the qRIXS?
So in qRIXS, I think we have probably on the order of, we measure 1 photon out of 10 to the 10th that fall on the sample.
Okay.
Right. So we have tens to maybe up to 100 photons that we measure in a second on our detector.
Got it. There it says per MeV.
Yeah.
That's I was confused. The MeV there is after scattered, after energy spread.
What MEV here, the way I've scaled is to say, let's say our beamline is transmitting 20 MEV pulses, if you scale it this way. Yeah.
And the other question, and I think you gave the answer, but it went over my head. So these time dependence of the zero order peak.
Yeah.
And it looks not uniform. And what is the explanation for that?
So what you're seeing here is, imagine that you're looking basically at this spectrum, but from above, right? So this peak here is just the elastic line, maybe with some contribution from some phonons. What you see, this hump here, those are magnetic excitations, and those are DD excitations. So we knew from a previous experiment that was done many years back that if you are close to the charge density wave peak of this material and you photoexcite the material, then you very easily perturb this charge density wave order, which will result in the decrease of the intensity of the elastic peak. So that's what we're measuring, in fact, here. So the system is basically in a combination of being in the density wave state, but it's also in a superconducting state. So yeah, you're literally kind of melting the density wave order, and you see how it kind of recovers on the order of a few picoseconds.
Okay, and should we take one more, and I'll shut up.
Yeah.
If we look at the second peak, should we take the differences that we see versus delta, the delay, as physical?
On this peak here?
Yep.
Well, so what this plot is showing you is that you can see that the intensity before time zero and after time zero is about the same. So all I'm trying to say here is that for at least the photoexcitation conditions that we used here, which is fairly low energy, both in terms of photon energy and fluence, we don't really perturb the DD excitation much.
Thanks.
That's all. But there were other experiments that people did see changes there, or people saw changes in the magnetic excitations and so forth.
So I had a question about your liquid target chamber. I was curious what kind of base and operating pressures you achieve and how you tailor the differential pumping to preserve the vacuum in the neighboring components.
Yeah, so when we don't flow anything in the chamber, it's kind of in the low -7, upper -8 range. When we start typically flowing the sheet jets that Jay can probably tell you a lot more details about that, we get usually low -4, upper -3 millitorr range. So when we basically stabilize the operation, so we know that the jet is not going to, well, there's always a chance that it can freeze and spray and do all sorts of things. But when we kind of reach a relatively steady state, then we open the valves to the rest of the beamline, and we basically have differential pumping, several long apertures, and eventually one of these shear pumps, XIA, that probably every synchrotron has plenty of those around too. But those are really good because they are really one long aperture with ion pumping in there. So they can maintain something on the order of 4 orders of magnitude difference. So we are, again, let's say a millitorr in chemRIXS, then we are in the -5 scale, like a couple of meters upstream. But then on the other side, we easily maintain -9, maybe even -10 without perturbing it at all. And then we have, the usual kind of, protection system around this thing, tied to gauges and all that, so that if the jet does go bad and, start spraying liquid everywhere and the pressure rises, the valves would close and all that. But yeah. And then usually after an experiment, we need to open that big door. Somebody goes in there, wipes things up. Especially if the sample is, of course, corrosive or, anything that might be of some hazard, then we need to be even more careful. But it requires regular maintenance to kind of make it compatible. Yeah.
Any more questions?
Okay, this will have to be the last one, I'm afraid. Thank you.
Thank you, Georgi, for the talk. Was wondering, your energy resolution you mentioned here, is it limited by the instrumentation, by the optics, or by the detector? My other part of the question is, any improvement you expect in the future, would instrumentation bring you? What would you envision can improve your performance of the beam on the detector side?
Yeah, I would say that at the moment, it seems like we are limited by the line density of the grating that we have in our spectrometer. So it's 1,500 lines per millimeter. The right people can simulate very well what you should expect from that, and we currently match what we're getting there. That's not to say right away that once we get our better grading, we would immediately get to that higher resolution, because we don't quite have an independent way, for example, to tell you what's coming from the monochromator. That's one contributing factor. Another contributing factor will be how well the beam is focused on the sample, because this is the source of our, we think we're focused well, but again, we don't have a particularly good way of saying, are we actually on the 5 micron scale or are we 20 micron scale? So we might having some issues there that we're just not sensitive yet, but we will become sensitive in the future. On the detector side, we do single photon kind of counting and centroiding and try to get as best as we can there. But I think that one way to get even better is to probably mature to maybe a CMOS sensor, which now are starting to kind of show up with direct detection in the X-ray range. So those have really kind of good signal to noise ratio, so that you can maybe centroid even better and get even, and the pixels are really small, 3.5 microns. So we have path towards ensuring that we will get the ultimate resolution, but I cannot tell you at the moment which exactly is going to be the critical factor, just because we're not quite there yet.
What about time resolution?
What about
Timing resolution on the
timing
detector side.
resolution? Yes,
Is it
timing
needed?
resolution gives us sleepless nights, especially from the fact that I mentioned kind of in passing this arrival time tool. It works well when you have strong X-ray pulses because then you can kind of tell shot by shot what happens. When we squeeze our exit slit to 5 microns, the pulses are not so strong anymore. So we need to accumulate over many events to see signal, which means that you cannot correct for jitter over these events. We also know that there are a lot of ways that the system can be improved much upstream from us. There are signals that are traveling kilometers that maybe need better, timing stabilization, temperature stabilization, and all that. So it's a big project that I cannot tell you that, I will be able to solve this thing myself. It's really a facility type question, but we want to be, below 100 femtosecond. Mostly because, okay, our pulses are already maybe stretched to about that level, but a lot of the kind of the interesting non-thermal states that you might be able to access, those don't live for a long time. If you want, they'll be there for a few picoseconds, and then maybe everything is going to kind of look as if you have just, turned the temperature on and the system is just heated up. So it's going to be a long process for us, but I think ultimately we'll get there, but it's challenging.
Thank you.
All right, let's thank our speaker again.